Hi, everybody. It's Professor Mitchell. We're finishing up Chapter 6 today on rational numbers and proportional reasoning. And today we'll be talking about proportional reasoning. We'll talk about ratios and their relation to rational numbers, proportions and their properties, constant of proportionality, and we'll talk about scaling and bar models. A ratio is used to compare quantities. It's usually written as A to B or A over B, and can be used to represent part to whole, or whole to part comparisons. And here's an example of that. There were 7 males and 12 females in the Dewdrop Inn on Monday evening. In the game room next door were 14 males and 24 females. So they want us to express the number of males to females at the inn as a ratio, which would be an example of a part-to-part ratio. And then they want us to express the number of males to females at the game room as a ratio, which is also a part-to-part ratio. The number of males to females at the inn is 7 to 12, since there were 7 males and 12 females. And at the game room, it's 14 to 24, which simplifies to 7 over 12. So proportionally, the proportions of males to females were the same at both places. Now they want us to express the number of males in the game room to the number of people in the game room. So this is an example of a part to whole ratio. And since there were 14 males and a total of 38 people, that ratio would be 14 to 38 or 7 to 19. That brings us to proportions. A proportion is a statement that 2 given ratios are equal. So it's a type of equation. If A, B, C, and D are all real numbers and B and D do not equal 0, then the proportion A over B equals C over D is true if and only if A times D equals B times C. I think we might have mentioned this earlier in the chapter as an example of a way to determine if 2 fractions are equal. So you can also use this in proportions. This is called cross-multiplying. Allie and Benty type at the same speed. Allie started typing first. When Allie had typed 8 pages, Benty had typed 4 pages. When Benty has typed 10 pages, how many has Allie typed? So notice it says they type at the same speed, and Allie started typing first. So this is an example of an additive relationship. Students should be able to reason that since the 2 people type at the same speed, when Benty has typed an additional 6 pages, because they started out having typed 4 pages, and then later they were up to 10 pages, so they typed an additional 6 pages. When Benty has typed an additional 6 pages, Allie should have also typed 6 pages. So she should have typed a total of 8 plus 6, which is 14 pages. Here's another example. Carl can type 8 pages for every 4 pages that Dan can type. If Dan has typed 12 pages, how many pages has Carl typed? This is an example of a multiplicative relationship. So the 2 people are not typing at the same rate. Since Carl types twice as fast as Dan, that's given by this first sentence, he will type twice as many pages as Dan. Therefore, when Dan has typed 12 pages, Carl has typed 24 pages. Here's another example. If there are 3 cars for every 8 students at a high school, how many cars are there for 1,200 students? So we'll use a proportion to solve this problem. So we'll say 3 is to 8. 3 cars are to 8 students as X cars are to 1,200 students. 3 is to 8 as X is to 1,200. And then cross multiplying, we get 3 times 1200 equals 8 times x. So that gives us 3600 equals 8x. And if you divide both sides by 8, you get that x is 450. So if there are 1,200 students at this school, that means there are 450 cars. The constant of proportionality. If the variables x and y are related by the equation y equals kx, which is equivalent to saying k equals y over x, then y is proportional to x, and k is called the constant of proportionality between y and x. A central idea in proportional reasoning is that a relationship between two quantities is such that the ratio of one quantity to the other remains unchanged as the numerical values of both quantities change. So this ratio that remains unchanged is your constant of proportionality. So that's the number k that we were talking about in the previous slide. So as long as you change x and y both at the same time, sort of at the correct rates, then this ratio will remain unchanged. All right, so now we'll use the scaling strategy to determine which is the better buy, 12 tickets for $15 or 20 tickets for $23. So here's how the scaling strategy works. The scaling strategy for solving the problem would involve finding the cost for a common number of tickets, which would be the least common multiple. So now we're going to find the least common multiple of 12 and 20. Think about that for however long you need. Turns out that the least common multiple of 12 and 20 is 60. So now, if we bought our 60 tickets under this deal, 12 times 5 is 60, so that means 15 times 5 would be $75. We would pay $75 for the 60 tickets under this plan, or multiply this number by 3. 20 times 3 is 60. 23 times 3 is 69. So under this plan, 60 tickets would cost $69. So the second plan is the better deal. Another way to solve that problem is to use the unit rate strategy. So now we'll use the unit rate strategy to determine which is the better buy, 12 tickets for $15 or 20 tickets for $23. The unit rate strategy for solving this problem involves finding the cost of one ticket under each plan and then comparing the unit cost. In the first plan, since 12 tickets cost $15, then one ticket would cost $1.25. You get that by doing 15 divided by 12. In the second plan, since 20 tickets cost $23, then one ticket would cost $1.15. That's from 23 divided by 20. So again, the second plan is the better buy. Another example, Kai, Paulus, and Judy made $2,520 for painting a house. Kai worked 30 hours, Paulus worked 50 hours, and Judy worked 60 hours. They divided the money in proportion to the number of hours worked. If they all earned the same rate of pay, how much did each earn? So let's let X be the unit rate, or the rate of pay per hour. Then 30X would denote the amount of money that Kai received. And Paulus would receive 50X, because then and only then will the ratios of the amounts be the same as 30 to 50 as required. Similarly, Judy received 60X. I think they kind of over-explained this part a little bit, maybe. The total amount of money received is 30X plus 50X plus 60X. So that amount has to equal 2,520. Those three terms add up to 140X. And since 140X equals 2,520, that means X equals 18. So Each person's rate of pay is $18 an hour, which means that Kai received 30 times 18, which is $540. Paulus received 50 times 18, which is $900. And Judy received 60 times 18, which is $1,080. Equivalent ways of writing proportions for any rational numbers a over b and c over d, with a and c not equal to 0. Actually, in order for this to work, none of these numbers could be 0, a, b, c, or d. A over b equals c over d if and only if b over a equals d over c. In other words, two fractions are equivalent or equal if and only if their reciprocals are equal. So what I get out of this slide is just that there are different correct ways to set up proportions. Another way to do it is, instead of writing a over b equals c over d, you can write a over c equals b over d. Ratio and proportions are used in scale drawings. The scale is the ratio of the size of the drawing to the size of the object. For example, the floor plan of the main floor of a house in the figure is drawn to this in the scale of 1 to 300. And they want us to find the actual dimensions of the living room in meters. So in the floor plan, the width of the living room is 2.5 centimeters and the length is 3.7 centimeters. So all you have to do to determine the actual dimensions of the living room is to multiply those two measurements by 300. So 2.5 centimeters times 300 is 750 centimeters, which is 7.5 meters. That's the width of the living room. And the length of the living room is 3.7 centimeters times 300, which is 1,110 centimeters, which is 11.1 meters. So the actual dimensions of the living room are 11.1 by 7.5 meters. All right, I believe this is the last example. The ratio of 8th graders to 7th graders at a meeting is 4 to 7. So the first question is, if 1/4 of the 8th graders are boys and 2/7 of the 7th graders are boys, what is the ratio of boys to students at the meeting? And then the second question is, if there are 9 boys at the meeting, what is the total number of students? So a bar drawing is perfect for this problem. All right, so here we have, in the first part of the drawing, 1/4 of the 8th graders are boys. So they've divided this part into 4 parts and shaded one of them. So there's the 1/4 that are boys. And then the other part of the diagram is divided into 7 parts and 2 of them are shaded. So that's the 2/7 of the 7th graders are boys. So that means that out of the total 11 parts in the diagram, boys are represented by 3 of them. So that means that the ratio of boys to students, which is another part to whole ratio, is 3 to 11. All right, and then for the second question, it said if there are 9 boys at the meeting, how many students are there total? So if 3 units in the diagram represents 9 boys, then 1 unit represents 3 boys. Therefore, the total number of students is 11 times 3, which is 33. And that takes care of chapter 6. We'll see you next time for chapter 7.